Right now it's recording. All right, so we were talking about, I brought the slides from previous class. So we're talking about vibration absorbers, right? We said, well, in general, vibration suppression is just we're trying to suppress the vibration, as the name says. I'm trying to protect the device from steady state harmonic disturbance at specific frequency. I said we saw vibration isolators before when we were talking about transmissibility. We even did a project on that, how to protect some type of electronics from base excitation. Now we're talking about vibration absorbers. Now, I said vibration absorbers, in this case, dynamic vibration absorbers, as if you want to go with the full name. We are going to stick with the simplest one. We're gonna just go with the simplest one, which is basically a mass and a spring. So if we have a spring mass system under some force vibration, we want to know how can we absorb the vibration of the main structure, that mass m, by adding an extra spring and mass to the system. Right? In this case, we called it ma as the mass of the absorber and ka as the stiffness of the absorber. We derived the equations of motion. Right, a little bit of math there. We found the amplitude of displacement, right, for the structure, and amplitude of the displacement for the absorber. Right? So these are the functions of frequency of the excitation omega, mass of the absorber ma, mass of the absorber, and amplitude, stiffness of the absorber, stiffness of the main structure, and the amplitude of the force applied to the system. Right? We said force is, we are assuming that's just the harmonic force F naught sine omega t, F naught being the amplitude of the force. Now, X is the amplitude of displacement for the structure, XA with the amplitude was the amplitude of the absorber. Now, using the equation for X, we said, well, the goal for the absorber is to make sure that when we apply the force to the main structure does not move that much, right? Or doesn't move at all. We are supposed to suppress or absorb that vibration. So whatever vibration is caused in the main structure should be absorbed by the absorber we're adding to the system. To ensure that X should be 0. So we put X is equal to 0, and we found the frequency. The excitation frequency, the relationship, there to say, between the excitation frequency and the properties of the absorber. Right? Now, if we look at that relationship, we see that that is actually the natural frequency of the absorber. If you think of the absorber as just a spring mass system, natural frequency of the absorber is the square root of Ka over Ma. Right? And we see that omega turns out to be the same thing, the relationship between omega and the properties of the absorber. So the conclusion would be, when you design an absorber to absorb the vibration of the structure at a specific frequency, the natural frequency of your absorber should be equal to the frequency of excitation. Right. Now we use that, we plug it into the steady state solution for the absorber, and we found the displacement of the absorber. If we design an absorber for that specific frequency, then XA, X lowercase a, T, would be the absorber's response to the force vibration applied to the main structure, right? XAT. That's how the added mass is going to move if the absorber is designed specifically for that excitation frequency. And F naught over Ka would be the amplitude of that motion. We said the reason we want this is that because very frequently we have this constraint that the mass we add, the spring mass we add as the absorber, the motion of the mass should not exceed some limit, and that's why we need to know this displacement absorber and make sure that we stay within that limit. Right? We meet that constraint when we are designing our absorber. Now, that took us to the next stage. That we said, well, this is an absorber. It's good, right? It's going to absorb the vibration, but we designed this for a specific frequency. Right? Let's say I designed this for 20 radian per second. I'm assuming I know exactly what my external excitation is. Some force is applied to my main structure with 20 radian per second as its frequency. And I designed the absorber for that frequency. Now, in that frequency, this absorber is going to perform pretty well. Now, the question is, in reality, the excitation frequency is not going to stay exactly that on that number, right? It's going to deviate a little bit lower and higher. So we need to know how would our absorber perform under other frequencies that are not exactly the frequency of the excitation. So if the driving frequency shifts a little bit, right, we want to know how does the absorber perform. We also mentioned that we have to be mindful or cautious about when we add this spring mass system, we're converting our system from one single degree of freedom system to a system of to a 2 degree of freedom system. Right now we have two masses, so it's a 2 degree of freedom system, and we're going to have two natural frequencies. So we have to make sure that the operating frequency, the excitation frequency, is not also very close to these any of these natural frequencies, because if it is too close to those natural frequencies, we're going to have resonance, which is not good, which means we're going to have huge displacement, right? Very similar concept for single degree of freedom system. Is the resonance is the same for 2 degree of freedom system with 2 degrees of freedom. If we excite the system with a frequency close to one of these natural frequencies, then we're going to have large displacements, which that's what we don't want. That's what we're trying to avoid here, right? That's why we designed vibration absorber. Let's answer this question now. We got up to this question. We said, well, how much deviation in driving force the absorber can tolerate or can handle? You design absorber, you want to know how good is that, you know, if how robust this vibration absorber is. So let's take it from there. Now I'm going to define, well, you've seen it already, or these are not new concepts, but I'm just going to put them here. I'm going to define 3 parameters. Omega p would be a square root of k over m. And what is that? Well, it's the original frequency, natural frequency of the primary system, right? Original natural frequency of the primary system. Right? The system before I attached the absorber to it. Right? It was just a spring mass system. It had some mass and had some stiffness. I called it primary system. Before that, it has some natural frequency, right? I called it omega p, natural frequency of the primary system. Just to emphasize, before attaching the absorber. Omega A, we've already seen that, Ka over Ma, that would be the natural frequency of the absorber, right? Natural frequency of the absorber that we actually attach to the system. So this is before attaching, let me just put it this way, before attaching to the primary structure. Are there primary system? Let me just be consistent. Primary system. And the last thing I'll define is mu. This is just mass ratio, Ma over M. I'll call this mass ratio. There's no unit, the mass of the absorber over the mass of the structure of the system, a primary system. All right, now I'm going to use these definitions. Let's start with X. right? The value of the equation we got for x, all the way there, this relationship, right there. Oh, this is xa, so this one. Let's bring that to that slide. Ka minus me omega squared f naught. So x would be this fraction Ka minus ma omega squared f naught. The denominator was k plus Ka minus m omega squared k plus Ka minus m omega squared multiplied by Ka minus ma omega squared. Ka minus ma omega squared minus Ka squared. Here's what I'm going to do, a little bit of moving things around. Right? Let's move this. Let's write this in this way. I'm going to take 1 Ka from the numerator out. So that becomes, let me write it this way. That becomes 1 minus ma over Ka omega squared. And from the denominator, I'm going to take 1 Ka and 1 K out. So I'm going to take 1 Ka out of this. I'm going to take 1 Ka out of this. This becomes 1 minus ma over Ka omega squared. I'm going to take a K out of this. This becomes 1 plus Ka over K minus m over K over omega squared. So I'm going to take 1 K and Ka from the first term, and the second term I'll do the same thing. Take 1 K and 1 Ka out. So that becomes K, Ka. Now, from the first term, we'll get 1 plus Ka over K minus m over K omega squared, right, times 1 minus ma over Ka omega squared minus, well, let me continue this right there, Ka over K. So all I did, I just took Ka from the numerator and another Ka from the denominator, right? So these two can be canceled out, this Ka and Ka there. Now let's see what can we do. I want to use the terms that I defined to rewrite this equation. I have a term ma over Ka. I have one here, and I have another one there. Let's see how can I write it from based on what I defined, based on these three terms. I'm going to write it here. Ka over ma. Let me start with actually a different term. Let me start with Ka over K. Ka over K. Well, Ka would be ma omega a squared, right? I got it from here. I square both sides, then Ka becomes ma omega a squared. K would be m omega p squared. Right, I got it from this term there. Right, square both sides, K would be M omega P squared. So I can write this as MA over M is mu. So this becomes mu times omega A over omega P squared. So that would be Ka over K. Right? I have two of that. One Ka over K here, one Ka over K there. So I can replace these two with mu omega A over omega P squared. Now for MA over M, what can I do there? Well, let me write it here. MA over Ka. MA over Ka, I can get it from this relationship. This term I define natural frequency of the absorber before attaching to the primary system. If you square both sides, MA over Ka would be 1 over omega A squared. You square both sides, take MA to the other side, numerator, Ka to the other side, denominator, and omega A comes to the denominator on the right side, moving things around. So I can write MA over Ka as 1 over omega A squared. So I'm going to replace all of these in this equation. The first one would be 1 minus omega over the numerator. So let me rewrite everything here. X. I forgot F not there, apparently. So this, I'm going to move K to the other side, Kx over F naught. So this becomes X K over F naught is equal to, let's put the long one, I need that. From the numerator, I get 1 minus omega over omega A squared. So numerator, I'll get 1 minus omega over, omega A is in the numerator. Omega over omega A squared, right? From the denominator, let's see, I'll get 1 plus mu omega A over omega P squared. Right? I'll get 1 plus mu omega A over omega P squared. Maybe I should have used bracket right there. There you go. And then I have minus M over K omega squared. Now M over K, I can just write it the same way I wrote MA over Ka. Right? M over K, this one, M over K, right, would be M over K would be 1 over omega P squared. And the same manner, if I look at this equation, square both sides, M over K would be 1 over omega P squared. So I plug that back. Would be omega over omega P squared. Minus omega over omega P squared. Right? First term. Second term, I have 1 minus, well, I said omega A over Ka would be, MA over Ka would be 1 over omega A. So this becomes omega over omega A squared. So this becomes 1 minus omega over omega A squared. I'm going to close this bracket. This is the second term. The last term, minus Ka over K, well, we said Ka over K would be mu omega A over omega P squared. So I'll just put it there. Minus mu omega A over omega P squared. So, after all this, replacement, now what I have the relationship between the force applied to the system, which is F naught, right here in the denominator. Xk, well, basically that represents the force applied to the primary structure, right? So I have the relationship between the input force, the magnitude of the input force, and the magnitude of the force tolerated by the primary structure, which is represented by xk. So this relationship is this whole fraction, long fraction you see here. This is force transmissibility function, right? Force transmissibility function. This tells me that for a given input force, like F naught is the magnitude of the input force, for a given input force, how much force my primary structure, which is the main structure I'm trying to absorb its vibration, how much force that structure tolerates. So how much of this force applied to the system is actually transmitted to the primary structure, right? If this is the primary structure M, this is F naught. I added this new spring mass spring damper here, spring mass here, K-A-M-A. Now, by adding this, I want to know now in this new configuration, how much of this force applied to this structure, main structure, is actually transferred to the main structure, and how much of it, as a result, whatever is not transferred to this M, is transferred to MA, right? So I want to maximize what is transmitted to MA and minimize what is transmitted to M. Right? I want my primary structure to tolerate less or almost zero force, and all the force I want to be transmitted to my absorber. Right? Because I want my absorber to absorb this energy that's coming from the external force. And my primary structure does not get any, it's just acting as something that is passing the energy to the absorber. So this is force transmissibility function. Now, from this, how do we answer the question that we're trying to answer, right? How much, we were trying to answer this question, right? How much deviation driving force the absorber can tolerate? Here it is. If this is the force transmissibility function, it means that if this xk over F naught, right, that xk over F naught, right, the magnitude of that, is greater than 1, which means xk is greater than F naught, it's no good. Because this is telling me that the force tolerated or transmitted to the primary structure is more than the force applied to the primary structure, which is horrible because I'm trying to get rid of this force. Right? Force applied to primary or main system, this is the input force, right? The magnitude of the input force. Or let me just be more excitation force. So no improvement here, no improvement. Adding that the spring mass system to my primary structure was supposed to absorb the energy from the external excitation force to improve my situation. So my primary structure does not go through some big displacement, does not have to tolerate a lot of force. If this happens, if the xk over F naught, the magnitude of it is greater than 1, it means adding that the spring mass system actually made the situation worse. The opposite of that would be, or the ideal situation would be when xk over F naught is smaller than 1. So result xk is smaller than F naught. So this is good. This is improvement, right? Improvement. This means that the applied force F naught applied to the primary structure, what my main structure or primary structure is tolerating, or what force is applied to it, whatever force is applied to it, is less than the force excitation force, meaning that part of the force has been transmitted to the absorber, or absorber is absorbing part of this energy. So my main structure is not receiving all the energy coming from the excitation force. So this is improvement. So if xk over F naught is smaller than 1, meaning that part of this excitation input is going to my absorber that I added to the system. So my absorber is improving the situation, right? I'm getting rid of at least part of the force. If I'm exactly on that frequency, excitation frequency that I designed the absorber for it, this would be actually 0. Like no force is applied to my primary structure. All the force is transmitted to my absorber. So let's draw this. Right, let's draw this one. I'm going to try to draw this function. Right there, this force transmissibility. If I draw it, you don't get always this nice drawing, but I'll give you the typical shape. I call this R being omega over omega A, frequency ratio. I define this as omega over omega A for this case. Remember, we had frequency ratio for basic excitation, for rotating on balance. There were always the relationship between excitation frequency and some frequency. In this case, I used omega A. In those cases, it was excitation frequency over natural frequency. And on this side, I plot absolute value of xk over F naught. If I draw this, right, for my system, again, not always this clean and neat and nice, but you'll get something along this line. It goes up, goes all the way up. This is, let's say, some natural frequency. Comes down, gets to 0. Goes all the way up again, some large magnitude, and then goes like this. This is the frequency we designed our absorber for. Right? This is where R is equal to 1. This is where omega is equal to omega A. Right? That's the design frequency. Also, for this frequency, we design it. So as a result, if you look at the force transmissibility on y-axis, it's 0 for this. This is the ideal case. So when the excitation frequency is it has exactly the same frequency as my absorber. All the force is transmitted to the absorber, so nothing is tolerated, or nothing is, no energy is going to stay in my primary structure. Now, how do we get the performance of our system from this? Right? Again, that was the main question we're trying to figure out. Right? When, for which range this absorber is good, and for which range of frequency this absorber is useless. I'm going to use what I just figured out here. Xk over F naught is greater than 1, no improvement. Xk over F naught smaller than 1 is improvement. So if I draw the line for, let's say x is equal to xk equals to 1, xk over F naught is equal to 1. Let's say this is my 1. That's where xk over F naught is equal to 1. So as long as I'm in this range, right, this range right here, below this line, I'm good, right? It means that in this range, my absorber is doing a good job. It's xk, let me put right here. For this range, xk over f naught is smaller than 1. So my absorber is performing well. Even though my excitation frequency is not exactly the design frequency, the natural frequency of the absorber that I designed to absorb this vibration, I'm deviating probably a little bit, right? Let's say the frequency excitation is not 20 radian per second now. It's 25. So R becomes greater than 1. Let's say I come here. It's somewhere there. Right? This is some where omega is greater than omega A. I designed the absorber, I put it there. Now the external force has a little bit of deviation in its excitation frequency, I still, if we come all the way right there, I'm still getting improvement. This absorber is still improving the situation, because if I didn't have the absorber, so if we didn't have the absorber, this would have been the original, I would say, system. If I want to estimate something, this would have been the original system. Goes all the way and then comes down like this. If I didn't have this absorber, I would have been here, right? Meaning that my xk over f naught would have been greater than 1, which means my absorber is well, in this case, no absorber. This means that I had almost, well, the old force would have been transmitted to my primary structure. Right? This is the original system, if you want to think about that. And this is the system with absorber. Right? So original system means no absorber. So that means that this range here from, let's use red color, from this right there to here, right? Let's call this R1 and call this R2. This point right there and this point right there. As long as I'm between these two frequency ranges, right, from R1 to R2, my absorber is actually reducing the vibration. If I go out of this range, my absorber is actually making the situation worse, and it's amplifying the vibration. Right? You can see xk over f naught is greater than 1. So adding that spring mass system to the absorber to the system makes things worse if I'm out of this range. This range is called bandwidth of operation. That is the bandwidth that the absorber operates well and it does the job it's supposed to do. The closer you are to R equals to 1 or omega is equal to omega A, the better, but you can deviate a little bit. So let me give you a good definition of that. R1 and R2 denote the bandwidth of operation for the absorber. Right. R1 and R2 obviously correspond to some frequency. So that would be, let's say R1 is omega 1 over omega A and R2 is omega 2, some frequency over omega A. So omega 1 and omega 2 are the frequencies frequencies that represent the bandwidth of operation. How do we find this mathematically? All right, you can't just plot this and find where, well, you can, but mathematically speaking, if you don't want to plot this, and by just knowing your transmissibility, force transmissibility function, how do you find this? I'll tell you exactly how it works. So to find the upper limit, right, omega 2, what do? You put xk over f naught equal to 1. Remember, that's the absolute value. So it could be equal to 1 and minus 1. At when xk over f naught is equal to 1, it means xk over f naught could be 1, or xk over f naught could be minus 1. Right? I plotted the absolute value here. So you make this equal to 1. The frequency that you're looking for is the maximum positive value of omega. To find the lower limit, you put xk over f naught is equal to minus 1, and your frequency would be the minimum positive value of omega. What do I mean? Well, when you make this equal to 1 or minus 1 in this force transmissibility, you get an equation to the order of 4. So it has multiple roots, positive and negative. Among those roots, the maximum positive value of omega would be your upper limit, and minimum, when you make it equal to minus 1, the minimum positive value of omega would be your lower limits. Let's take a look at an example. Maybe things get a little better. So we have a very standard form. Let's put it this way. This is example. I have a system there, mass M, sitting on some springs, K2 over 2, K over 2, just stiffness values. And I added a absorber there, MAKA. Some force is applied to this system, like somewhere. And it's a sinusoidal force, so it's a harmonic force. So F naught sine omega t. Here are the values you have. So the statement goes as find the value of mass ratio mu for the absorber and the bandwidth of operation. What do you know? You know F naught is equal to 13 newtons. Omega, the excitation frequency is 180 cycle per minute. You can convert that to radian per second by multiplying it by 2 pi over 60. If you do that, you'll get, I believe, 6 pi radian per second. Mass of the primary structure is 73.16 kilogram. K, which are the springs, which is the value of stiffness for the springs attached to the primary structure, is 2600 Newton per meter. XA, which is the amplitude, the amplitude of the absorber, displacement for the absorber. This is a constraint you're given. As I said, imagine that this spring, this is the this is a table measurement table that you're using for some sensitive measurement, and you want to make sure that it doesn't oscillate or doesn't vibrate. So you attach a spring damper, a spring mass underneath as the absorber. You want to absorb this vibration, so make sure that the table is steady. That is XA. You have a limited, you have a limited space there, and that limitation should be met when you're designing this absorber. So XA would be, what we're given is 0.2 centimeters. It's pretty small. Let me add a note. Maximum displacement of the absorber. All right. What was the equation for absorber? Just putting it here, it was XAT is equal to XA sine omega t. Right? That was the general form for the steady state solution. Now that's the XA you're given. All right, the last piece of information you have, I guess that's pretty much it. All right, so let's see where we start. We start with the constraint that we're given, right there at the end. This is the constraint. Now we know that XAT, or let's put it this way, that's how we designed the absorber. We said when X is equal to 0, right? That's the goal. We want the primary structure not to move or oscillate. We said we got XAT as minus F naught over KA sine omega t. Right? Remember that? That's what we got when we replaced, if I go back, actually we have it right here. There you go. Amplitude of the displacement of the absorber. Right? Minus F naught over K over sine omega t. That's when the displacement of the absorber at the design frequency. Now, I am given this information. Right? I know this. I'm given this amplitude. And I know F naught, so I can find, so I know now F naught over Ka is the amplitude. So I take the magnitude is equal to 0.2. So I can find Ka. F naught over 0.2. F naught is 13 newtons over 0.2. Let me just write it. 13 newton, 0.2 centimeters. It gives you 6,500 Newton per meter. So you got a Ka. Right? The stiffness that the absorber needs to have to be able to absorb the vibration for a primary structure under this excitation force. So we're designing the absorber, right? We found Ka. Now let's find Ma. We want to design this. We need to know what kind of spring we need to use, how stiff that spring should be, and you need to know how much mass you have to attach as the absorber's mass to absorb the vibration at this given excitation frequency, given excitation input. So this is the absorber's stiffness. That's how stiff it should be. Once we know Ka, well, we know omega A is equal to a square root of Ka over Ma. I can just move things around. Ma becomes Ka over omega A squared. What is omega A? Well, if I'm designing this absorber for this specific frequency, omega A should be equal to omega. Go back even, you can see it in the graph, right? R should be equal to 1. I'm designing the absorber to make sure that it absorbs the vibration for this given frequency. So this would be Ka, which I found, over omega A. Omega A would be omega. It should be that to be an effective absorber for this frequency. 6 pi squared. If you do this math, you will get 18.294 kilogram. That would be your absorber's mass. Absorber's mass. There you go. So now, if you add a mass of 18.294 kilograms to the primary structure using a spring with the stiffness of 6,500 Newton per meter, you can absorb the vibration for this specific input excitation, which is an excitation with 13 Newton amplitude and 6 pi radian per second frequency. And you're going to stay within the limit. The amplitude of your absorber is going to stay within 0.2 centimeters. It goes up and down. That's how we design this absorber. When we're asked to find mu, so mu is basically just the mass ratio, would be M A over M. Well, MA we found, which is 18.294, divided by mass is 73.16. That will give you 0.25. That's what you were asked to find. First part. The second part, you are asked to find the bandwidth of operation. Now let's do that. All right, see what does that look like. If I go to the next page. So to find the bandwidth of operation, I have to, what was I supposed to do? Remember I said I have to find X. The instruction was telling me, well, to find the upper limit, put xk over f naught equal to 1, and then find the roots. Maximum positive value would be the upper limit. Put xk over f naught equals to -1. Minimum positive value would be the lower limit. But to do that, I have to find a couple of things. If you remember the transmissibility function, I need to find omega A because I need these values to plug into my transmissibility function. Ka over Ma. I need omega P, which is the square root of K over M. I also need mu. Well, mu I already know. Mu is 0.25. If you plug in these numbers, this becomes Ka, we found it, 6,500 divided by 18.294. 6,500 divided by 18.294. This gives you seems like 18 point. Let me make it a little less crowded here. I'll rewrite this. 18.849 radian per second. And find omega P is the square root of K over M. Well, these are given in the problem. 2600 and M is 73.16. So 2600, 73.16. This gives you 5.96 radian per second. And we had mu from before. Not the right tool. There you go. So now let's form our xk over f naught. If I go back, all I'm doing is I'm replacing, well, omega is just a number, it's just a parameter, so I'll keep it that way. Omega A, now I know omega A, I know mu, omega, and omega P. So I can replace all of these. I'll get my function, transmissibility, force transmissibility function. If you do that, here is what you will get. 1 minus 0.002 0.28145 omega squared. Remember, omega, we don't have it. Omega is the range that we're plotting this function. Denominator would be 1 minus 0.0028145 omega squared times 3.5 minus 0.02815 omega squared minus 2.5. This would be your force transmissibility. Force transmissibility. So how do we find the upper and lower limit? Well, to find upper limit, make this equal to 1. Xk over F naught is equal to 1. You will get this equation. I'll write the general form. You will get 0.0002815 omega squared plus 1 minus 0.0028145 omega squared times 3.5 minus 0.28152 omega squared minus 3.5 is equal to 0. This is going to be an equation of order 4. You can find online tools. I'll share with you one after the class on the forum. You can just easily simplify this and get the equation in the general form as a fourth order equation and then find the roots. Now, once you find the roots, you can find the maximum positive value. And if you do that, your omega max, I call it omega max, becomes 21.07 radian per second. This is your upper limit. For lower limit, you take this, you put this in equal to -1. Actually, let me put to find the lower limit. You put xk is equal to f over f naught is equal to -1. I don't write the equation there, but all you got to do is just take this at the top and make it equal to just this side. Make it equal to -1, right? And then multiply both sides and move things around. You'll get the relationship. If you do that, from there, the minimum positive value would be 7.4. And that would be in radian per second. So from these two, you get back your bandwidth of operation. What is that? It's from 7.2 to 21.7. This is your bandwidth of operation. So within this range, your absorber is going to perform well. Let's see if in a few minutes I can just plot this and you'll see what is going on. Let me move this there. What is the force transmissibility? There. I'm going to plot the force transmissibility function. If I don't make any mistake, hopefully, plugging in the values. This goes from 0. Let's plot that to 40, maybe. Oh, maybe 40 should be good. Let's give 1,000. The equation, something divided by something. So numerator is 1 minus 0.0028145 times x squared. Remember, I'm plotting the absolute value, so I have to put ABS. That's the absolute value function in the graph. Numerator would be 2 parentheses multiplied by each other. The first one would be 1 minus 0.02815 times x squared times 3.5 minus 0.0 28152 times x squared, and I believe minus 2.5. Let's see if I did it correctly. All right. I hopefully did correctly. Let's just fit the, this would be x-axis. I don't want it to be all the way to the negative, so let's make it maximum to 40. Y-axis, you have to a little bit move around the limits to get a better view of. That's minus 0.1, and let's put this on 1.2. All right, maybe I moved this x-axis a lot. Let's give me some room there. This would be R, frequency ratio. Oh, this would be omega, actually. I'm plotting it as omega, not R. And the Y would be xk over f naught. Let's use grids, and I want to use more fine grids so we actually see what is going on. Show the grid, and let's go for 0.1 and 0.1. All right, look at this. I need to see the x-axis, so I'm going to move this a little bit, minus 1 to the left. There you go. So here is the range. You can actually see it. If I draw a line there, this is 1. This is line x is equal to 1. Xk over f naught is equal to 1. So here is the where my absorber is effective. This is the area that is effective. Going from this frequency to this frequency. What is this frequency? If I want to be more, let's do it this way. If I draw this line, it's about, this is the bandwidth of operation. This is what I get. It is from pretty much close to what we got. 7 point, what was the range? I got 7.4, right, somewhere around here. And 21.07. That's the bandwidth. Above this, doesn't work. All right. Let me stop that.